is probabilistic assessment of seismic bearing capacity of ship footings seated on heterogeneous slopes using finite element limit analysis, or FELA, and response surface method, or RSM. Next slide, please. And the table of content, you see that I will present some introductory remarks about the literature review and the basic concepts behind what we have studied. I will talk shortly about finite element limit analysis. Then we'll move to inherent variability, and finally we'll talk about response surface method and also reliability-based design, which will be the last episode of this study. Next slide, please. And the authors, you see, Hessam is my PhD student at University of Gilan. Sina, my nice friend from rock science. Youssef, also from mining one. Dr. Payan from University of Gilan, and myself, who have jointly contributed to this paper. Next slide, please. Seismic bearing capacity of shallow footings is a topic of great significance in the geotechnical engineering practice. It becomes more complicated when the foundation is placed on an earth slope. Homogeneity is a common assumption has been a common assumption in overwhelming majority of studies in literature. However, natural soil deposits usually come with inherent variability, and that means uncertainty in stability analysis is inevitable. Next slide, please. In this study, the lower bound theorems of finite element limit analysis, or FELA, using second order programming, or SOCP, along with the response surface method, have been adopted to evaluate the influence of random variability of underend shear strengths on seismic bearing capacity of a shallow footing seated on a heterogeneous earth slope. The so-called RSM has been deployed to avert the need of using copious Monte Carlo simulations. Next slide. And this slide shows schematic demonstrations of the geometry of the problem. You see that a shallow footing is sitting on the verge of a slope, which was assumed being non-homogeneous. And you see that pseudostatic horizontal earthquake coefficient is applied to the medium underneath. I mean the soil, the slope, and the width of the footing is 1 meter. The unit weight is 20 kilonewton per cubic meter, and the underend shear strength, which was assumed as the randomly variable parameter in this study, it bears the mean value of 80 kilopascal and the COV of 15%. Next slide, please. Finite element limit analysis, which is the backbone of the numerical calculations in this study. For doing so, the lower bound FELA theory was deployed. It states that 4 constraints must be met. Element equilibrium, discontinuity equilibrium, boundary conditions, yield criterion enforcement, which will be discussed shortly. Next slide, please. In this slide, you see that these 2 equations are the equilibrium equations for a 2D problem. And the first one is, contains the contribution of earthquake loading simply incorporated as a pseudostatic earthquake coefficient, KH in this equation. Next slide, please. And the discontinuity equilibrium to be satisfied along the interfaces of adjoining triangular elements That's the basic assumption in FELA, lower bound theorem, and induced stresses bound to take particular values at the boundary edges of the problem domain. It means boundary conditions. And finally, the yield criterion enforcement. It means more Coulomb constitutive law in this very study. And you see from the equation underneath that there is an inequality constraint which should be met throughout the optimization. Next slide, please. The vertical load component exerted on top of the footing is the objective function. And in this study, a maximization is sought in order to make an estimation, a limit state estimation of the bearing capacity of shallow footing, which is the integration of the vertical, the vertical normal pressure at the interface between the shallow footing and the slope. Next slide, please. Inherent variability, is conventionally taken care by Monte Carlo simulation in conjunction with random field theory. However, it is perceived to be time-consuming. Therefore, we chose to use surface response method in this study. Next slide, please. And you see this simple equation as also discussed by Bridget in a more comprehensive way. This is the basic form of response surface method, and you see that the different parameters in this equation are under and shear strength, slope angle, earthquake horizontal acceleration coefficient, KH. These three parameters are variable, and the distance ratio from the foundation to the slope was kept at 0. Next slide, please. And the coefficients of the RSM model after the regression analysis are in this table. Next slide. And this plot simply shows the correspondence between the numerical analysis, sorry, that's not FLEC, that's FELA, results in comparison with RSM predictions. Next slide, please. And for the random variable generation, we assume 1 million realizations of the under and shear strengths of the clay deposit. The mean value, as mentioned earlier, was 80 kilopascal, and its COV was 15%. And log normal distribution was assumed, homogeneous especially, but random through realization. That constitutes random homogeneity, or single random variable, as mentioned earlier by other presenters. Next slide, please. And the output, in this slide, in the left-hand side, you see that the realizations of the under and shear strengths versus the output, which was the ultimate bearing capacity of the shallow footing resting over the heterogeneous slope. Next slide, please. And in the reliability-based design concept, as discussed by Dr. Richard Batters, you see that we should define a performance function which is inside the parentheses of the first equation. You see that the Q alt, the bearing capacity of footing for each of those 1 million cases should remain larger than the applied service load. But the cases which fall under a lower that service load, design load value constitutes failure. So we calculate the probability of failure as the number of cases falling below the set limit, and then the reliability index will be calculated. Next slide, please. And this is a sample output from the results of this analysis. It will show, two types of plots are here. The left-hand side will show the probability of failure versus factor of safety, that nominal factor of safety or design factor of safety. And in the right-hand side, you have the reliability index or beta versus the same parameter. And you see that for a design, set uncertainty, acceptable uncertainty level, you will be able to choose the design factor of safety. And I will move on to the final slide, I presume. Yeah. The concluding remarks would be as follows. RSM corroborated being a robust tool to handle probabilistic analysis. Reliability index is a well-recognized parameter to mitigate uncertainty, and reliability index has got a direct link to PF, probability of failure, and steeper slopes demand higher design FS values to accommodate inherent uncertainties. Thank you very much.